Bhargav from Web3 Foundation, and today I'll be talking about random sampling. It's a technique that we've developed at the foundation for building trustless and efficient bridges. So this is joint work with Alistair and Fatime, also from the foundation. So yeah, let's get started, right? So what are bridges? I guess most of you already know bridges in the context of cryptocurrencies or like blockchains, but just to set the context right, bridges are like infra for interoperability, right, between independent and technically diverse chains. So blockchains have different consensus mechanisms, different networking layers, and so on. So it's hard for chains to interact or communicate with each other. And for this particular setting, what I really mean by bridges is that infra which allows one chain to fetch and believe the state of the other chain, right? So over here, like I've kind of given the example of Polkadot and Ethereum, where each of them have a state, and you want one of the chains to fetch and believe the state of the other chain. By the way, in this talk, I'll kind of instantiate with like Polkadot and Ethereum, but the techniques that I will be mentioning can be generalized to any proof-of-stake networks. And then interesting apps can be built over this basic functionality, right? So you can think of token swaps, migrating the state from one chain to the other, using the governance of one chain on the other, and so on. But this is like the basic functionality is that you fetch and believe the state of the other chain. And traditionally, bridges have been built using trusted intermediaries, right? So since the chains cannot communicate directly with each other, you have these centralized relayers who kind of like fetch the finality of one chain and push it to the other. And there is no way for the chains to verify or like validate the correctness of what the centralized relayer is providing, right? So yeah, it's like you're kind of blindly accepting a finalized block or like state without really verifying it. And this has several major flaws or issues, right? So one of them is like safety issues. So the centralized relayer can be malicious. So for example, like he claims that a particular amount of tokens has been burnt on one of the chains, but it's really not been burnt. And like, yeah, kind of mislead the other chain. The other issue is liveness issues, right? Because like these centralized relayers are kind of like single points of failure. So if there's like a denial of service attack or something of this sort, then the bridge gets halted because there's like only one centralized entity responsible for relaying it. And the third, of course, is like censorship. The centralized entity can selectively censor some messages over the other, which again like leads to bad user experience. So, and this so far has not been going so good, right? So yeah, if you are not like living under a rock, you would have already heard of a lot of hacks related to bridges. So these centralized entities are kind of the most vulnerable attack surface. And there has been like recent studies which showed that in like 2022 and 2023, more than half of all the blockchain related like hacks were like related to bridges. So what can we do about this, right? So we really have to kind of get rid of this like centralized entity in the middle. And before we discuss like how we tackle this problem, the first thing is to like really define what trustless bridges means, right? Like what are the requirements? So trustless is a relative term here. Like obviously you would trust the basic Byzantine assumptions of both the chains. But what you really want to do is that you don't want to have any additional trust assumptions on the intermediaries or relayers who are sitting between the two chains, right? Mainly for the safety of the bridge. So the first kind of requirement is that like, yeah, running these relayers has to be permissionless. So kind of like no stake has to be, no stake or like whitelisting has to be associated, right? Anyone can just jump in and start a relayer node and interact with the two bridges. The second is that any misbehavior has to be traceable back to the validators, right? So there's this like, yeah, saying that like, don't shoot the messenger, and relayers here are literally like messengers, moving messages between the chains. And anything that goes wrong, you have to kind of be able to catch hold of a validator on either chains and like be able to slash them. And third, of course, is efficiency and low latency, right? Like blockchains are resource-constrained environments, so you would want to have as efficient as possible design for these bridges. So the canonical way to go about this is to build trustless bridges via light clients, right? So light clients are basically kind of a lighter version of nodes in a blockchain, which do not have to keep track of the whole state, but can somehow, in a very efficient way, listen to the finality of what is happening on the chain. And that's like the most canonical way of like building trustless bridges. So, for example, on like the Polkadot Ethereum bridge, what you can do is like you can run a Ethereum light client as a parachain on Polkadot, which is like listening to the Altair light client protocol. And on the other side, you can look at running a light client of Polkadot on Ethereum as a smart contract on Ethereum. And this listens to finality on Polkadot, more specifically like the beefy finality, which I'll come to in a minute. And you have these trustless relayers who are just like relaying the messages and collecting fees for the work that they have done. So there's like no real trust assumptions on the relayers themselves. So yeah, I would like, if time permitted, I would have wanted to talk both the directions, but the more interesting direction is the one from Polkadot to Ethereum, mainly because it's so expensive to compute on Ethereum, right? So running a light client on Ethereum is very expensive, and that's why you would want to make it as efficient as possible, which brings in challenges. So let's say over here we have like the two chains, Polkadot and Ethereum, and we want to come up with like a light client running as a smart contract on Ethereum, which listens to Polkadot's finality. And the main challenge here is that, yeah, how do you make it as inexpensive as possible, right? To listen to this finality. To this end, we kind of have like two steps over here, right? And this is where like beefy comes in. So beefy, you can think of it as like two components. One is that you have like an additional layer of finality that we put on top of the grandpa finality on Polkadot, which makes it very easy for on-chain light clients to follow it, right? So this is really like you kind of push all the complexity of grandpa and have like a very simple additional round of voting. And for a light client to follow this finality, it just has to check if a particular threshold of validator signed it or not. And the second part is the random sampling protocol, which is an interactive protocol between the two chains, which reduces the costs while still retaining the security, right? And in this talk, I'll be mostly focusing about random sampling as a technique itself, but also in the context of Polkadot and Ethereum. So yeah, let's look at what this interactive random sampling is, right? So sure. Yeah, I mean, if it's like some clarifying thing, yeah, you can. Mm-hmm. No, it's basically like a smart contract that is running on-chain on Ethereum, which is listening to the finality of what is happening on Polkadot. So, but it's not like really storing the whole state of Polkadot in itself, but just like a commitment to the state. Yeah. So it's you like yeah. We have a bit fancier data structure, but yeah, you can think of it as a commitment to the whole state. Yeah, so you kind of keep fetching these new state commitments once in a while. So yeah, so when I kind of retrospectively looked at this interactive random sampling protocol, I felt that this was easy enough, like the core idea was easy enough to be represented as a comic strip, right? And that's exactly what I did. So over here you have basically a relayer, a trustless relayer, who, let's say like a block is finalized on Polkadot, right? So you have like a relayer who kind of fetches this block through the bridge to the smart contract on Ethereum, and he claims that he has, so like Polkadot right now has 300 validators. So he claims that this block has signatures of more than 201 validators, right? He just claims it. He doesn't reveal these signatures. And then what the smart contract does is, okay, it's cool, you claim that you have these signatures. What I do is I kind of use Randov. Randov is like a randomness beacon part of the protocol on Ethereum. And it uses this randomness beacon to randomly sample a bunch of these signatures, right? So it doesn't want to check all the 201 because that will be very expensive. But what it does is it randomly picks up, let's say, validator V2, V11, V49, V180, like 25 of these like randomly selected signatures, and then asks the relayer to kind of produce these signatures, right? And if the relayer is honest, like he will be able to produce these signatures. And the light client can then verify these signatures and update the state accordingly, right? So this is kind of like the very high level idea of what random sampling is doing. Yeah. Yeah, that's a good question. Something that I kind of skipped for simplicity. But basically, you have something like similar to warp sync, right? So the next validator set is kind of committed in the state of the previous epoch. So in a proof of stake network, you have epochs, and the validator set kind of like remains same in each of these epochs. And what you do is, like on Polkadot, for example, the last block of the epoch will contain a commitment to who the next validator set is going to be. And yeah, and then it kind of like, bootstraps from there on. And so you always have this chain where you know who the next validator set is. Yeah. Sorry, I couldn't hear you. No, but that would then be like within the assumptions of the Byzantine fault tolerance of Polkadot itself, right? So yeah, so it's like we have this trust assumptions on Polkadot, like the Byzantine assumptions. Yeah. No, so yeah, so you would have to like either like start from like the beefy genesis, or if you have like a trusted checkpoint, then you can start from that trusted checkpoint as well. Yeah. 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 So yeah, I guess like I'll kind of like give a bit more like technical detail of this high level idea that I shared, right? So let's say like Polkadot has 3f plus 1 validators where f of them are failing or like malicious, right? So this over here, I'm kind of representing like a message sequence chart between the relayer and the light client on Ethereum. So the relayer would like, collect all these like 2f plus 1 beefy signatures, and then like make this claim saying that, hey, I have these 2f plus 1 signatures on a particular block, and also share one of the signatures. So he just claims that he has like the indices of the validators, but very importantly, you also need this one like signature, because this is the one who, we'll catch hold of if something goes wrong, right? And then the light client uses Randao to randomly sample M of these signatures. And kind of, so this is like a very typical commit challenge response protocol, right? So you have the commit phase, you have the challenge phase where you are asking this randomly sampled signatures, and then you have the response phase where the relayer like responds with these particular M signatures. And then, yeah, the light client verifies if these signatures are correct and accepts the block. So if you notice over here, like the crucial security parameter is this M, right? Like the number of signatures that you're randomly sampling. And the if you, I mean, I don't want to go into the math, but if you carefully look at it, the probability of the light client kind of being duped is exponential in the number of, reduces exponentially in the number of signatures that are sampled. So the more number of signatures you randomly sample, the more sure you are that what you're getting is actually correct, like probabilistically, right? So then the question now is like, how do you derive the security parameter, right? So the crux of the security analysis, yeah, is really like deriving this parameter M, which regulates the trade-off between the security and the efficiency of the protocol. And what we have over here is like a crypto-economic argument, right? So we assume that any adversary would be rational. So he would only launch an attack if the expected value of the attack is positive, right? So what we want to really ensure is that this expected value is negative. And what is the expected value of the attack over here? It's basically like, yeah, the probability that he is successful in the attack, which is exponential in M, times we assume that, yeah, if the attack is successful, he really gets like the market cap of one of the chains. And 1 minus P is the probability that he loses or he's not successful. And the slash. So this slash is the slash that is applied to the validator who kind of like signed in the initial like commit phase, right? And we want to ensure that like this is negative, and that is how we derive the parameter, the security parameter over here, right? So this is, yeah, like the most simplest version, but we kind of not looked at all other angles as well, right? So there are a few more additional considerations when we are doing this analysis. And because like we assume that the protocol is one shot, right? But it's interactive. So there are like two aspects. One is that there are like certain concurrency issues that can pop up, which increases the probability of an attack success. And the other is the randomness that is used by the light client on Ethereum is biasable, right? So there are ways where if the validators on Ethereum, for example, collude, then they will be able to create some bias on this randomness. So I'll like dive a bit deep into the first issue, right? So the concurrency issue. Yeah, let's kind of take a look at this a bit deeper. So you have this one relayer, let's say like a malicious relayer, and he has like some stake of a particular validator behind him, right? And the key insight over here is that only like one of these validator gets slashed, and it takes a delay to slash a validator. So the slash is not instantaneous. So even if a validator is caught, it takes some time to really like slash him. And this is something that adversary could exploit, right? So what a malicious relayer could do is he just like spins up n number of relayers, all with the same backing validator, such that his chances of like succeeding increase without really affecting the stake that is at risk. So that's how he's like able to increase the chances of him kind of winning this like random roll of die through Randao, right? And we have a interesting solution for this. So what we do is we do something called dynamic sampling, right? So the idea here is that once you notice that a lot of these relayers are being spawned, you dynamically increase your security parameter, right? So this has like two advantages. One is that if there is no attack, then your security parameter remains the same, so it doesn't affect your efficiency. only when an attack is detected or like launched, you dynamically increase your security parameter. But the nice thing is that it is logarithmic on the number of relayers being spawned. So yeah, so you would kind of know the number of relayers because so it's really not the number of relayers that is relevant, but actually how many times for a particular block height are relayers bringing in with this initial commit. Yeah, so yeah, I mean, so the smart contract kind of keeps a map of like which relayer is trying to like update which block height. So yeah, so it's like logarithmic, right? So the relayer would really have to like spawn a lot many relayers to like a malicious entity would have to spawn a lot many relayers to increase this like signature checks. So yeah, and yeah, I mean, you could kind of think of that, yeah, there might be some like griefing attacks possible as well, but we kind of do an analysis to show that griefing attacks here are like too expensive. Okay, cool. So what's like the status of this work? So Snowbridge is currently live, and it is secured by the random sampling BFI that we talked about in this talk. So yeah, you can kind of like play around with the app. I think like right now it just supports like ERC20 tokens, but like a more generic version is kind of work in progress. And yeah, like to conclude, like what does random sampling really achieve, right? So it achieves like trustless and permissionless relayers. So the relayers don't have to put any stake or anything. So this kind of increases the decentralization aspect as well. And the running a relayer is not computationally intensive, right? So you don't need like any specialized hardware or anything to run relayers. The second is like, yeah, the bridge design supports like arbitrary dApps. So it's really about just like fetching the finality of one chain on the other. So you can be creative and build any interesting applications on top of it. And yeah, in terms of like efficiency, like the gas costs, for example, of running the light client smart contract on Ethereum are comparable to snark-based approaches, right? And very importantly, this scales well even if the number of validators increase. So let's say Polkadot has 300 validators now, but even if it has 1,000 validators, the efficiency of the bridge is not going to be affected. And it's all backed by robust cryptoeconomic security arguments. Right? And for future directions, we are thinking of applying like the fiat Shamir heuristic to remove this interactiveness between the parties. And this would allow us to have a lower latency in the bridge. Another point is that there's already been quite a bit of research at the foundation for accountable light clients. So there's already a paper, you can take a look at it on the foundation's research site, where there's a snark-based approach using aggregate signatures to have like an accountable light client. Yeah, and finally, less trust, more truth, right? This is one of the promises of Web3, and I guess we are going a step closer, at least in the domain of bridges. Thank you.